In chapter 12, we're talking about the details of reinforcement, how we place reinforcement, how much length we have, spacings between bars, hooks, bends, all of these different things that we have to care about during the placement of reinforcement to allow us to cast concrete properly and to allow us to have the section that is desired for our design. So this chapter is an overview of the ACI 318 requirements and the detailings of reinforcement. Some of the clauses we also have from the 2011 version, and you guys are encouraged to read more in the code because we will not be able to encompass everything in one chapter or in a couple of classes. Now, the first thing we're going to talk about is the bar bend. Now, a lot of times we have to bend our bars, right? And to be able to bend our bars, whether this is a 90-degree angle or a 135-degree angle or any angle, there are requirements in the code that we have to follow. Before that, we need to understand that reinforcement shall be bent cold. Somebody might preheat the reinforcement. That's not allowed unless it is permitted by a licensed professional engineer for a specific reason. But otherwise, if there's no reason to bend on hot, then we should always do our bending on cold. Field bending of reinforcement partially embedded in concrete is not allowed, except if it is shown in construction documents or permitted by a licensed design professional. And that means that you cannot really cast your concrete, place your reinforcement, and then apply the bending afterward. The main reason for this is because bending changes the shape of the bar. So once it is cast, once concrete is surrounding the bar and it's embedded inside, you will, by bending it as it is inside the cast, by bending it, you will change the shape of the bar, and you will loosen the bar and you will reduce the bond between the bar and the concrete. In other words, if I have a bar that will stick out like this and it will bend like this, make sure that you bend this bar before you cast this member. Okay? You don't cast the member and then bend the bar. Now, unless this was permitted or shown in the construction document, which happens a lot, or this was permitted by a licensed professional engineer that sees that this is the only solution for a specific situation. Now, standard hooks is one of the forms of bars that were bent. Those standard hooks, either they're seismic hooks or just cross ties, they have to have a minimum depth of embedment inside. They're used for the development of deformed bars in tension, and they shall conform to this table, 25.3.1. They're described in terms of the inside diameter of the bend because the inside diameter is easier to measure than the radius of the bend. So when we're looking at bending such a bar, here's our bar. We look into the diameter of the inside bend, not the outside. Why? Because it's very easy to measure this. This is what you bend around. You place an object and you bend around it. Okay, now let's look at this table, table 25.3.1. Here's the table, and it tells you that if you're going to get a standard hook, this is called a standard hook. You can do any other hook, but it's not going to be a standard hook if it is not following that table. Now, in terms of distances, the hooked part after the bend, the hooked part after the bend is called L extension. That L extension equals to 12 diameter of the bar. If it is 90-degree hook, this is a 90-degree hook. This is a 180-degree hook, right? We can bend either 90-degree standard hook or 180 degrees standard hook, depending on the space that you have. Which one is better? they're both good. They both do exactly the same job. But of course, it's easier to bend 90 than to bend 180, right? And in this case, you will require some more space. So if I'm bending and I don't have much space, then probably 180-degree hook would be a better one. Okay, how much is this L extension? L extension very clearly starts after the bend is done. So it's at this point down. That L extension equals to 12 times the diameter of the bar. Okay, so if I'm phi 25, I multiply 12 by 25, not by the area, by the diameter, and then put this as the L extension. Okay. Now, as far as the minimum inside bend diameter, which means this diameter, this is the diameter of the object that you bend around. Okay. How much is this? They said this depends really on the bar size. My bar size 10 to 25, 6 dB. My bar size 29 to 36, 8 dB. And then 43 to 57, 10 dB. Okay? So you really have to conform to this, which is the object that you bend around. Right? You don't bend on anything. Now, what if I reduce this? What happens if I get a smaller diameter object and I bend around it? What will happen is you will end up stressing your bar so much, you might even yield the outer and the inner part of the bar. So if you don't really conform to such diameters as you bend, you might be able to yield your bar before it's even used. So that's not really a good practice. And then the same thing applies to the 180 degree, 6 dB, 12 dB, and 10 dB. Going to the L extension of the 180. Now the L extension here comes completely after your round. You did a complete round around your object. Now what is remaining is the greater of 4 dB and 65. Of course, this is much smaller than the 90 degree because already the 180 degree hook is a strong hook, right? They really have a lot of pressure on the concrete that it will hold itself before it slips out. Now, getting into the minimum bend diameter. Now, what's the difference between this and the previous table? This is just the minimum bend diameter, which means it is not the standard hook. This is just the bend diameter. So anytime you bend anything, whether it's a tie, it's a hoop, it's a stirrup, you have to follow those bend criteria. Now, for a 90 degree hook, for a 135 degree hook, and for a 180 degree hook, those are the standards. Your extension goes to 6 dB or 75, 12 dB, and then here 6 dB or 75, 4 dB or 65, depending on the hook degree and depending on the bar size. Okay, so and again, the same thing applies to the diameter of the inside object that you use to bend around. 4, 6, and then 4, 6, and then 4, 6. Okay, depending on the bar size. It has less stringent requirements than the standard hook. The standard hook is really, really important because the standard hook you can rely on to get your LDH. Where's the LDH here? If I go back here and show you, it shows you here something called the LDH. And this is the development length of your bar inside the concrete that is required to get the full strength of the bar. And we will talk in detail about this when it comes to the development length. While here, it doesn't really show any L development. You see, it's just any bend. This here is for any bend that you use. Okay? So we need to really differentiate between what we mean with a standard hook and what we mean with a minimum bend diameter in general. Okay? Surface requirements. The bar surface requirements at the time of concrete is placed. The reinforcement to be bonded shall be clean of ice, mud, oil, or other deleterious coatings that decreases bond. So you need to see the reinforcing bar really neat and clean, right? if you see so much rust, it's acceptable to have rust or corrosion, but if you see so much of it that really affects the bar diameter, then this is not acceptable. If you see things that are sticking on the bar that may reduce the bond between your bar and your concrete, then you should not accept it. Okay. The use of epoxy coating in accordance to this provision is permitted. Materials used for protection of pre-stressed reinforcement against corrosion in unbonded tendons are not considered to be contaminants as described in this provision. This is a little bit more detailed about specific type of reinforcement called the pre-stressing strands or pre-stressing reinforcement. Now our next part is the tolerance on D. What is the tolerance on D? Now as we go to the construction site, remember that we had, this is my concrete beam, for example, right? And then this here is my steel reinforcement placed inside, right? I want you to think about someone who's had his reinforcing bars changing this D. Remember this D here, all the way to the center of the bar. If this was D, now you go to the site and you see sometimes they place the reinforcement completely off where it should have been, right? So you see your reinforcing cage maybe coming this way. Right? So now you've reduced your cover on the side, you've reduced your D, right, which reduces the capacity. Now, how much tolerance can I accept? How much of difference between my old D and my new D can I accept? They said if the D itself is less than 200 millimeters, then you can only accept the tolerance of 10 millimeters or 1/3 of the specified cover. So the cover is 40, 1/3 of the 40 is about 13 millimeters, right? So the smaller of these. If it is more than 200, then you can only accept 13 or 1/3 of the specified cover. Okay, so what we see a lot of times is the cover going to 0. That's not acceptable, right? Especially if you know that this member will be subjected to external external environment and not going to be very protected, then in this case you shall refuse to continue with the cast, because all of these, if we look at this, we only look at this right before casting, right? After they place concrete and right before casting. So what you need to be aware of is that ACI allows for the changes in D, a little bit of a change, but that change should not be much. This part we talked about before is the minimum spacing requirements between our reinforcement. So generally speaking, what do I need for, or what am I looking for when I'm placing two reinforcements next to each other? I want to be able to flaw my concrete nicely and easily between them, right? And I want to ensure that there's not a big space between them that could cause cracking, either due to shrinkage or temperature cracks. So the code has this minimum spacing requirements. The first one is to have a 4/3 D aggregate. 4/3 means 1.33, right? 1.33 of the biggest aggregate size, which is what we specify the aggregate with. And then the second one is for parallel non-pre-stressing reinforcement placed in 2 or more horizontal layers. Remember when we had a beam that looks like this, we had reinforcement here and reinforcement here. Now that spacing between them shall be not more than 25 millimeters. Okay? And then for longitudinal reinforcement in columns, now in columns I have, this is my column section, I have reinforcement that looks like this. This spacing here, the boundary elements of the wall as well, if I have a wall, and those are the reinforcements of my wall, that spacing. The clear spacing between the bar, remember it's clear, shall be the greater of 40 millimeters 1.5 D bar or 4/3 D aggregate. Okay, so I have a minimum spacing here between the bars in the columns in the vertical elements or in the walls as well. Now, bundled bars is another type of, or is another way to increase my size of diameter, while in the same time keep good spacings between them. What do you mean by bundled bars? Remember, if I have a lot of reinforcement within one column, if I have so much reinforcement like this, I might end up having very small spacing. So they allowed us to have what we call a bundle. So every 2 bars, bundle them together. So you wrap the bars together and they become 1 bar. So here is my bundle, next bundle, next bundle. What's the benefit of this is you will have bigger spacing here between the bars. And you can treat those 2 bars as if they are 1 bar. Okay? Now how much can you bundle? That's the first one here. The groups of parallel reinforcing bars bundled in contact to act as a unit shall be limited to 4 in any one bundle. Is that clear? So I cannot bundle 5 bars together. I can only bundle up to 4 bars. So you can basically have this shape as your maximum shape. You can have also this shape. What is this? Only 3 bars. And you can have, of course, a bundle of 2, but you cannot have a bundle of 5. Okay? Bundle bars shall be enclosed within transverse reinforcement. So you cannot really, again, the remaining of it, bundle bars in compression members shall be enclosed by transverse reinforcement that is at least number 13 in size. So the first one tells you that you shall have your transverse reinforcement around all the bundles, like this. Okay? So you don't come at one point and you say, okay, I'll place 1 inside and 1 outside. This is not allowed. Okay? All your bundle has to be inside your transverse reinforcement. Okay? And if you're bundling, then this here, at least it is phi 13. Okay? Cannot be less than phi 13. Bars greater than number 36 shall not be bundled in beams, because then it becomes really big bars and bundling them becomes as if you're not really bundling them. Every bar will just act on its own. Individual bars within a bundle terminated within this span of flexural members shall terminate at different points with at least 40 dB stagger. Now, if you're terminating the bundled bars, make sure that you don't terminate all of them together. You don't stop all the bars together. You stop some and you continue other ones, okay, until you reach your end of the cage that you're looking for. The development of the bundled bars, we will talk about development length in a few minutes. We treat the whole bundle as one equivalent bar diameter. So we see all of the bundles and we have an equivalent one big bar that gives the same area. So I will have D bar equivalent. Okay? Now this is 3 times the area, and this here shall give the area here shall be equal to pi over 4 dB squared. These 2 areas shall be the same. Okay, so you have an equivalent area, and that equivalent area will give you the equivalent bar diameter. Now, the development length, if we're developing the bar inside concrete, this is my concrete, that development length that I calculate when it comes to bundled bars, I have to increase it by 20% for 3 bar bundle and by 33% for a 4 bar bundle. Okay? So I calculated L development and then I have to increase it. So I multiply it by 1.2 for up to 3 or for 3 and 1.33 for a equivalent for the 4-bar bundle. Okay? The next part says that a unit of bundled bars, now the unit of bundled bars, those guys together, will be treated with an equivalent bar, an area equivalent to the bundle, and a centroid coinciding with that of the bundle. The diameter of the equivalent bar, call it dB, will be used in these things. What are those things? Spacing requirements, how far my bars are from each other, right? Cover requirements, what is my concrete cover? Spacing and cover values in 25.4.2.2, confinement term in this, and calculating my factors for my development length. We will look at these factors in a few minutes when we go into the development length. This is the psi. And then when it comes to lap splicing is what, when I have a terminated bar and then I'm taking another bar for it for either tension or compression, that lap splice, that distance, will be treated for not the bundled bar diameter, but for the individual bar within the bundle. And then it will increase in accordance with 25.6.1.5, which is this increase, 1.33 or 1.2, depending on the number of bars in the diameter, or the number of bars in the bundle. Bar splices in a bundle shall not be overlapped. The bar splices within a bundle shall not overlap. Entire bundles shall not be lap spliced, which means I cannot get all the 3 bars. You see how I overlap those 2 bars? This is called a splice, right? Now, if I'm getting 3 bars bundled together, right, I cannot bundle them with another 3 bars. I cannot lap splice them with another 3 bars. This is not allowed. Okay? Then what do I do in this case? There are ways to do this. We terminate one, and then we splice, staggering them one by one. So one will continue, one will stop. One will continue, one will stop, and so forth. I've seen this before. For example, we've done this in some of the bridges. We can do something similar to this. Right? Now what is happening here? You terminate a bar somewhere, and then you continue with another bar. Now what you will find is that this is not enough. Then you can add another bar to cover this part, right? So you're ensuring that at every time you have a full bar or full 2 bars in full strength. Or the other option is, what we had done before also, is to weld this part and this part, what we call the groove weld or the butt weld, front to front, to make sure that you have full strength within your splice. Now going over the concrete cover. The concrete cover shall be specified in accordance to this table. Let's take a look at this table. We've looked at these concrete covers before. If it's cast permanently against the ground, like footings, you're 75. Exposed to weather and contact to the ground, you have, depending on the bar sizes, either 40 or 50. Not exposed at all, like slabs and beams inside the building, you can go with 40, 20, or 40 for primary reinforcement, stirrups, ties, spirals, and hoops. Here, the second table here is for the cast-in-place pre-stressed concrete. What is pre-stressed concrete? Those are concrete members that are subjected to some compression before placement or after placement as post-tension members, like what we use in bridges. And those will have some differences, very few differences in specified covers, right? And you will see that the differences is not much, but that's if you're working on a pre-stressed member. That pre-stressed table shall be used instead. Now this one here is for concrete members that are manufactured in a concrete plant, like under plant condition. So it is more and more quality controlled, right? And then in this case, we have better requirements than if it is cast in place in the site, obviously because of the quality control. For bundled bars specified, concrete cover shall be at least the smaller of A and B, the equivalent bar diameter of the bundle, or 50 millimeters, right? So you take all the requirements before and then add to those requirements that you cannot exceed the equivalent bar diameter or 50 millimeters. For concrete cast against and permanently contact with ground, you shall go with the 75 millimeter all the time. Now we're talking about corrosive environment in the code. We're just touching on this. We kind of understand what the code is and how the code is dealing with the corrosive environment, harsh environments. It says in corrosive environments or other severe exposure conditions, the specified concrete cover shall be increased as deemed necessary. Now, how much of an increase? It doesn't really tell you exactly how much of an increase you will have. It leaves you, or it leaves it up to you. Remember that the concrete cover specified in the code is the minimum concrete cover. So by the time you'll see that you have some severity in the exposure, like sulfate, like freezing and thawing, like water, like sea, like creeks, all of these things you can, as an engineer, you can specify a higher concrete cover in order for you to protect your rebars. And then they had those exposure categories in this table, table 19.3. It tells you that the exposure, or depending on the exposure, we have different categories. And they called it several classes. And then you go over these classes, you will find that you will have more severity in different classes than other ones. And in this case, you will, as an engineer, you will have different requirements for your concrete cover. Remember, that's an important note, that reinforcement with rust shall be considered satisfactory, provided that the height of the surface deformations are not less than the applicable standard limits. And there are some standards to judge whether or not you have those violations of the limit or not. Getting into the ties, that's an important part of understanding how we can distribute our ties. Now, ties shall consist of those closed loop of deformed bars with spacing in accordance to A and B. The clear spacing is at least 4/3 D aggregate. The center to center spacing shall not exceed the least of 16 dB, 48 dB, and the smallest dimension of the member, right? Remember that the 16 diameter of the bar is the diameter of the longitudinal. The 48 diameter of the bar is the tie diameter. Okay? This is tie, this is longitudinal. And then we talked about all of this before in the concrete, in the columns chapter. And then we said that the number 32 or less, we use number 10. Number 36 or more, we use number 13 ties. We also talked about this. And then we went over a very important part when we said that we have to either hold every bar or every other bar depending on the spacing. There is no third option. We're either holding every bar or we're holding every other bar. If the clear spacing between the bars is less than 150, then we have to hold every other bar. If it is more than 150, then we hold every other bar. Then we said rectilinear shall be arranged for this 150 clear spacing alongside between in the two sides. It is also important to understand if you're holding the bars, you have to hold it with an angle that is not exceeding 135 degree, because in this case, if you're too wide, you're not really holding the bar. It will not prevent it from buckling out. Okay? So you need to understand those requirements and get into some practice with this. Those are some of the shapes we have. I don't really prefer having such a shape, which is splitting my column into two different cages. I don't really like it. I would like to always have this one nice big hoop that takes all the cage together. So I don't prefer having this. Such bars are really good and nice and handy. It allows for the placement of the concrete inside the column very easily. Those cross ties are really easy to place, right? They can be placed after the ties are placed. A lot of times we alternate the cross ties hoops, but it's an important question here. Why do they look like this and not look like this? The reason for this is to be able to place it, because your bars will be fixed in place, and you would want to have this nice 90-degree to be able to place it inside your cage after your cage is done. Okay, and that's it for the ties. It's very important to practice on how to place the ties, because the columns are very important members in your building. Development of reinforcement is basically how much amount of length of the reinforcement you would need to avoid the slippage of the bars. Okay, so if we're talking just development, meaning just straight bar, here's my concrete. And here's my bar. It's sticking inside the concrete, right? If I pull out on this bar, what are the expected types of failures? I am expecting, number one, to rupture the bar, right? So that means the bar is very bonded. There's a really good bond here. And this is deep enough, this is big enough, that it avoids the slippage of the bar. Number two is to break on the concrete. So you have something like this. That means you pulled out the concrete with you. So the bar was much stronger than the concrete, and the concrete will be pulled out. This is the second failure. Those two failures are good failures. Why? Because they are strength failures. They have to do with the strength of the bar, which is this here, and the strength of the concrete, which is this here. But then the third failure, which is really, really bad failure, this is if I failed the bar in slippage, which means the bar is pulled out like this. Right? Now, this is the failure I cannot accept. Why? Because you will design everything for what you believe is your strength, but you have something that is really bugging you. Think about it this way. I bought a shoes. The shoes is very comfortable. The shoes is very athletic. It has cushions. It's like perfect for everything. But the size is not right. You will not be able to wear it, right? So you got the perfect shoes, but it doesn't fit you. So this is exactly what happens. You would have a beam like this, and that beam sticks out of a column. Let's imagine this is the column, this is the beam. I have the perfect amount of reinforcement to take my load, right? Everything looks good, but then at the end, instead of breaking on the beam or crushing on the concrete, you slipped out here, and this guy got out of the concrete. This is really, really unacceptable. So for this reason, they came in the code and they decided to put provisions for development length, LD. The calculated tension or compression in reinforcement at each section of the member shall be developed on each side of that section by embedded length. So we have to have some embedment. Or we can hook it or add heads. Heads like what? Like at the end of the bar, here's the bar, you would add some type of head, because this provides a lot of bearing on the concrete to avoid the pulling of the concrete, of the bar. Headed or a deformed bar, or mechanical devices, or a combination between all of those. So we have to develop by certain way to ensure that it will never slip out. Now the hooks and the heads shall not be used to develop bars in compression. Those hooks don't work in compression, they only work in tension. Same applies to heads. Development length do not require to have a strength reduction factor. So whatever the given LD is, the length will be taken as is. We don't reduce it. It's already factored. And then the values for square root of f prime c and development length shall not exceed 8.3 megapascal. This is the value of square root of f prime c. Okay? Now let's go to the development length of the bar. It is calculated based on this provision, the greater of A and B. This provision, 25.4.2.2 or 0.2.3 or 0.2.4, where it has the factors. So the factors in the 2.4 would be used for the 2.3 and 2.2. We will look at this now. Or 300 millimeters. So by any means, if you get an LD that is less than 300, we use the 300. Okay? So let's put this at the back of our minds. We cannot develop a bar less than 30 centimeters. That's about the ruler that you guys have, the 12-inch ruler that we use. Okay? Now what are those provisions talking about? Is here. Now, you need to really understand how to use this table. If you're going to give me some focus, give me now your focus, right? What is this table talking about? It talks about 4 cases for 2 columns and 2 rows. Here are the 2 columns and the 2 rows. Now, when you're looking at any development length problem, you will use one of the 4. This, or this. Okay? Now, what are those talking about? The first column is number 19 or less. The second column is number 22 or more. Simple. So we know which column to use. If it's number 16, 516, I go here. If it is 525, I go here. Okay? And so forth. Now for the other one here on the side, I have those 2 that talks about clear spacing. What is this? It tells you simply, if you have enough clear spacing between your bars and between the bars and the cover, then you choose the first row. Okay? Now what the first row talks about is first part here, this part is for the beams and the columns. The second part here is for the slabs. So if I write this down here, that first part is for beams and columns reinforcement being developed, and the second part here is basically for slabs and maybe walls as well. Now if you don't fulfill the good spacing, those here are good spacing, then you have to go with the other case, which is poor spacing. Now which one gives higher values? This one gives higher values. Those guys here will give you a higher value. And this here gives you the lower value. Why the lower value? Because you already have good spacing between the bars. If I have enough spacing between each bar and the next bar, I have good spacing. I have enough spacing between the bar and the concrete cover, then I go with the larger values. If I have my bars really close to each other, if my bars here in the beams, for example, they're really close, then in this case I go with the second part. Okay? How do I check this? I have to check those 3 values. For the beams, I have to check the distance between the bars are bigger than GB. The clear cover for the bar is bigger than GB. And throughout the development length, my stirrups and the ties fulfill the code requirements. If I have all 3 of those information given, I go with these values. If they're not fulfilled or I don't have enough information, then I go with those values. Very simple and straightforward. Now let's go over those factors. The first factor in this equation is, of course, I have F yield. can see here, F yield and dB. This is F yield, and I have dB. Those are very simple. We know that the diameter of the bar and the F yielding strength of the bar. Let's go over the other ones. The other one we have is this lambda. Lambda here is the lightweight factor. If I have lightweight concrete, this provides a less of a bond with the concrete. So the best one is the normal weight concrete, which is our normal concrete. Then lambda equals 1. For lightweight concrete, lambda equals 0.25. Okay? For FCT and some specification, if you're specifying some lightweight concrete, then you have to go with in accordance with this provision that is not covered now. But generally speaking, once you see a lightweight concrete, your lambda is 0.75. Next factor is psi E. What is this? It has to do with coating the bar. If I want to protect my bars, one of the ways to protect them is to have epoxy coating. Those epoxy coating, they reduce the bond between the bar and the concrete. Okay? And in this case, if it is uncoated or just galvanized, which keeps it the same texture as a regular steel, then it's 1. Now if it's just zinc coated or galvanized, we call it galvanized, then it's 1. If it is epoxy coated or epoxy and zinc and epoxy dual coated reinforcement, for all other conditions it's 1.2. Now if it is epoxy coated or zinc and epoxy dual coated, that means it is zinc coated and epoxy coated, which sometimes is used with very high corrosive environments. In addition to poor spacing, like I have a clear cover that is less than 3 dB and clear spacing that is less than 6 dB, in this case we really increase the value and make it 1.5. So this is psi E. Going to psi S and psi T, that depends on the bar size. If I have really big size, I keep it at 1, phi 22 or larger. Phi 19 and smaller, I go with the smaller size. Then it reduces the LD. And then the last one is the psi T, which has to do with the casting position. What does this say? It says that if you have more than 300 millimeters, this is 30 centimeters, of fresh concrete cast or placed below horizontal reinforcement, then you take the 1.3, otherwise you take it as 1. So for all vertical bars, it is 1. For horizontal bars, if I have my bar laying out like this is my bar here, right? And I know that I'm casting as much concrete as more than 30 centimeters underneath this bar, then I take less of a bond, and then I take more of an LD. So the LD becomes 30% extra. What's the reason for this? Is they found that if you pour so much concrete under the bar, remember what do we do in concrete once we cast it? We vibrate it. Now that vibration, the more concrete you have, the more air bubbles go out, right? Now those air bubbles, if you have that much of concrete underneath the bar, which is, we said, 30 centimeters, then there will be some accumulation of those bubbles on the bars from underneath. And that reduces the bond. So for a horizontal bar, which basically comes in maybe a raft or a slab or a beam, if that bar has more than 30 centimeters concrete underneath, automatically my LD gets increased by using the factor of psi T being 1.3. Simple. Now if it's a vertical bar, that does not apply. If it's a bar that is down here, that also does not apply. So this guy here gets a psi T equals 1.3. Where is the psi T? If you go back to the equation, you'll see it at the top. And then they said that the product of psi T and psi E should not exceed 1.7. So if it goes more than 1.7, you take the 1.7 as your maximum value. This method is the second method to calculate the development length. We will not cover this method. It involves some other factors that has to do with confinement. So this is the confinement term. Like how much confinement, how much stirrups do you have around it? And then you have to go over calculating KTR, ATR, S and N. And we will not cover it, but it's for your reading. This here is for reading to know the other method. The more used method is the method that we talked about, the 4 equations that we use. They are straightforward. Now they developed even tables to get into the table and find the development length for each bar right away. Now this is continuation of it, and we're getting into an example here. What is this example saying? It's in all structures with normal weight concrete, lambda equals 1, uncoated reinforcement, so now the zinc coated or uncoated, zinc just galvanized or uncoated, our psi E equals 1, number 22 bars, bottom bars, that means psi T equals 1, with F prime C equals 28, grade 420, my reinforcement LD is 47 dB or 72 dB. What's the difference? 1.7 and 1.1. So the difference is the good spacing, this is good spacing, and the poor spacing. Right? Now, see the difference? This is around 50 dB, this is around 70 dB. Thus, as long as minimum cover dB is provided along with the minimum clear spacing 2 dB or a minimum clear spacing of dB for the minimum clear spacing dB, depending on whether it is a slab or a beam, are provided along with minimum ties and stirrups, then LD is about 50 dB, and the penalty for spacing bars closer or providing less cover will be that you increase the 50 dB or about the 47 dB to a 72 dB. Now, instead of looking at straight bars, we're going to start looking at hooked bars. Hooked bars are either 90 degrees or 180 degrees. Now, the development length for a hooked bar is not called LD, it's called LDH. LD, hooked. Okay? Now, the development of LDH, we get it from this provision. That's in tension, huh? And it is the larger of those 3 values. So every time I do it, I have to compare those 3 values together. Number 1 is 0.24 F yield psi E psi C psi R divided by lambda square root of F prime C times dB. A lot of times people forget to put the dB here. The second one is 8 dB and the third one is 150 millimeters. Remember, in the straight bars, it was a minimum of 300. For the hook bars, it's a minimum of 150. 15 centimeters is your minimum. Looking at those, I have to read the provisions, or especially those here. I have to read the provisions in 25.4.3.2. So we go there. A little bit different. I have normal weight concrete 1, lightweight concrete 0.75. This is for lambda. Going to the epoxy coated, now I don't have the 1.5. I only have 1 and 1.2. Okay? This is for uncoated or only zinc coated, and that one is for epoxy coated and then dual coated epoxy and zinc together. Now I'm going over to the cover. If I have good cover, it's 1. Poor cover, it is 0.7. What is defined as poor cover? It says that for number 36 bar and smaller hooks with side cover normal to the plane of the hook, larger than 65 millimeters, and for a 90-degree hook with cover on bar extension beyond the hook more than 50. What's the difference between side cover and beyond the hook? Now looking at the hook in a 3D, now this here is, let me draw it better than this. This is my hook here, and it's going to go down, okay? If this is the hook, my side cover is here and here. My extension or extension beyond hook is the one beyond the hook, which means if I look, what is the beyond the hook? It will be the one I see here. Now if I have this enough, good enough, this is more than 50 millimeters, and I have the side ones, which are those guys, more than 65. Then I can take psi C as 0.7. The next one is psi R, which is the confinement or confining reinforcement. If I have good confinement, which means I have enough stirrups that are confining this nice hook, whether it is ties for columns or it is stirrups for beams, then in this case I can take it 0.8, otherwise I take it as 1. Reading this, it says for a 90-degree hook, these provisions apply. For a 180-degree hook, these provisions apply. It says that enclosed along LDH with ties or stirrups perpendicular to LDH, at least the spacing is less than 3 dB. So the spacing between each tie and the next tie, or each stirrup and the next stirrup, is less than 3 dB along LDH, okay? And then enclosed along the bar extension beyond hook, including the bend within ties or stirrups, to L extension is less than LDB as well. And then the second one also says the same thing, but with LDA, within LDH, I'm enclosing it within ties and stirrups perpendicular to LDH at S less than 3 dB. There will be some shapes that will show you this. Here's how it looks like. So within the LDH, the stirrup spacing is less than 3 dB, and then the very first one is less than 2 dB. If I fulfill this within the LDH, then I have good spacing between good confinement. Otherwise, you're not well confined, and then you will have to put the larger value for the psi. Now, an important part that we need to know, that if you want to develop full capacity of the bar, you have to use full LDH or full LD length. Now, if you are going to have less stress, so in case that you know that the stress will go less, then your AS required, remember what's AS required? AS required is up to failure. I can reduce LD, my LD can be reduced with a factor called AS required divided by AS provided. Again, what does that mean? It means that, for example, I need 3 phi 16. Okay? But I did not provide 3 phi 16, I provided 4 phi 16. Then my LD can simply be LD times 3 over 4. Why is this? Because I placed amount of reinforcement that is 4 while I only needed 3. Then I can reduce my LD. Let's remember something important on this. My LD is the required length to develop the stress in the bar. Am I pulling from here? Here. I'm pulling here. Tension that will make my stress go all the way up to F yield. This is where I'm yielding this bar. True? The stress at the very first point equals what? 0. Do you agree? And the stress at the end of the bar equals what? F yield. Then within my LD, here's my LD, I should be developing what? From 0 all the way up to F yield. True? And we'll assume some linear relationship here. So the more I get away from the beginning of the bar, the more I get more stress. Makes sense? Makes sense. All the way at the end of the face of the concrete, I get my full strength of the bar. Very simple. Like, what if I'm not going to get F yield? How do you know you're not getting the full? Because I already provided much more reinforcement than what I needed. Then in this case, I will never reach F yield. Then all I need is maybe less than F yield. I will need something like this. So they said, in case you provided extra reinforcement than the required, you can reduce your LD to the ratio of AS required divided by AS provided. That means the provided is bigger. So this will be a factor that reduces your LD. Maybe 80%, 90%, give or take. Makes sense? And then the other shape of the hook bar, if it's confined in the perpendicular to the hook, it's the same thing that applies, which is the spacing being less than 3 dB, and the first one is less than dB along the extension length of the hook. This is normally happening when you are confining with column ties, confining the beam reinforcement being developed with hooks. And these are the provisions that talk about it. Okay, the development length of hook bars. And here is for the edge of a cantilever. You also need to provide some confinement to make sure that your confining psi is the higher value. And then our next one is the development length in compression. So the same concept with what we talked about before on development length in tension, we also need to have some development length in compression, which means if my bar is subjected to compression, which is normally the case with bars of columns, for example, these are compression members, right? Those compression bars that are subjected to some tension here, some compression here, they need to be developed. We cannot just rely on bearing. So that development length, we call it LDC, LD in compression. If the bar is under compression, the development length follows the biggest of these two criteria. What are those two criteria? Is 0.24 F yield psi sub r divided by lambda square root of F prime C dB, and then 0.0043 F yield psi r dB. And then we compare the biggest of those two with 200. Remember, in the development length and tension, we used to compare things to 300. Now we only are limited to 200. So by any means, this should not be greater than, sorry, should not be less than 20 centimeters. That's if the bar is subjected to compression. Now going to defining the factors inside these equations. This is the table 25.4.9.3. We have again, the lightweight concrete definition. We take it either 0.75 or 1, right, depending on whether it's lightweight or normal weight. Most of the concretes we use is normal weight, so we go with 1. In case lightweight is used, and we have a specification of FCT, then we have to go to the provisions in Chapter 19 and find out how to calculate lambda. The other one is the confining reinforcement. Why do we talk about confinement in compression or compression members? Because confinement in compression members is very, very critical. What it does is actually it makes the compression member columns or ties very sturdy, much stronger. The more confinement you have, the better confinement stress, the much better performance these group of bars will do with you. So in case you have good confinement, this is what I call a good confinement, then you go with the 0.75, which means you can reduce your LDC a little bit. Otherwise, you just take it as 1. What's a good confinement? Good confinement is if you have a spiral reinforcement that is used for confining, or you have a circular continuously wound tie with a DB, that's the diameter of the bar, bigger than 6 millimeters, and a pitch, which is the distance between one circular hoop to the next circular hoop, is 100 or less. And then number 13, or MD 130 wire, that also ties with a spacing less than or equal to 100 millimeters on spacing, or hoops with less than 100 millimeters in spacing. So that means you have good confinement, then you end up with psi r 0.75, otherwise it's 1. A reduction in development length, this applies to all of what we talked about before. All the provisions in 25.4.2.1, 0.3.1, 0.6.1, 0.7.1, and 0.9.1. They are permitted to be reduced by a factor equals to AS required divided by AS provided. Which means if we provided extra rebars than what is required for the analysis at the yielding point, then you can have some reduction in your length. Your LD could go lesser than what you calculated. And those modification or modified lengths shall not be less than the respective minimums in those provisions. What is the B, 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 and C? Those are the provisions that gives you the minimum. So when you go to the minimum, you cannot go less than the minimum. So if I go back and look at the minimum, you'll find that we're always comparing to 300, we're always comparing to 200, and comparing to 150, right? The 300 is the development length, the 200 is the development length in compression, and the 150 is the development length in hook bars, right? So you cannot go less than this. If your reduction gets you down below those guys, then those guys dictate. That's a very important part to keep in mind as you reduce your LD. And to be honest, it's not really important to reduce the LD unless you're very congested in space during the detailing at your members. So during the detailing, if you're really, really congested, you might be able to increase your bars and reduce your LDs accordingly. It is not also permitted at a non-continuous support or a location where anchorage or development for F yield is required, or where bars are required to be continuous, like where they really have to be, they're giving one another forces, headed or mechanically anchored, deformed bars, and in seismic force resisting systems, we don't reduce LDs simply because they will be subjected to cyclic loading going back and forth that can disturb the anchorage between the bar and the bond between the bar and the concrete. Last part we're talking about is the splices. What is the splice? Is when you've ended your bar and you want to continue this bar to keep going within your member. Now the lap splices are the most commonly used types of splices. People use welding or mechanically used mechanical couplers, threaded couplers, grouts, with couplers with grouts. All of these are more expensive methods to splice your bars, and if they're to be used, they're to be used in very, very limited and critical cases. So otherwise, what you would go with is a lap splice. What's a lap splice? It's simply your bar ended like this. Then you would bring another bar, and it continues from where your bar ended. That splice is the splice length. So this is L, I think they call it LDS, L development splice. And then you just tie them with the regular wire ties that you all know about and used in the lab. And then the lap splice, minimal clear spacing between the contact lap splice and adjacent splice or bars shall be in accordance with the requirement of individual bars in 25.2.1. Some provisions about the lap splices is for non-contact splices, inflection members, the transverse center to center spacing of spliced bars shall not exceed the lesser of 1/5 the required lap splice length, and 150 shall not exceed, shall not be bigger than, you shouldn't have big of a distance between your spliced bars and the next spliced bars. So that distance here should not be bigger than the lesser of your lap splice divided by 5, which is 1/5 of the required lap splice, or 150. So you shouldn't have big distance between the splices. Reduction in development length in accordance with this provision that we talked about is not permitted in calculating lap splice. You cannot reduce the lap splice distance. Remember, we talked about AS required divided by AS provided. That does not apply to splice length. And then lap splices of bundled bars shall be in accordance with 25.6.1.7. It's a hassle to splice bundled bars. That's why they have a special provision for it. Lap splices of deformed bars and deformed wires in tension, you have LST. Lap splice length, I call it LDS, should be LST. For deformed bars and deformed wires in tension, it shall be in accordance with 2.1, which is this provision, where it tells you that your maximum percent, look at this, lap splice is depending on the class of your splice. We have two types of classes. The first class is called Class A. That's, if you want to call it, it's a good lap splice. So Class A is a good lap splice. And Class B is the regular lap splice. We have to understand, if we're doing a lap splice, are we in a Class A or a Class B? Okay? Now, Class A, if we will know together now what Class A is. Class A, your lap splice length equals to the development length. Simple. So it is 1 times LD or 300, which is the provision for LD. Agree? And now for the Class B, you are the greater of 1.3 LD or 300. Okay? So it is the greater of 1.3 LD or 300. Now, how do we know Class A or Class B? Now, looking here, it tells you the maximum percent of AS spliced within the required lap length or lap length is 50% for a Class A and 100% for a Class B. What do you mean by this? It means if I get back to this picture over here and I started splicing everything within the same section. So now I'm splicing. I keep just putting the bars coming. This is a break line. This is a break line. Imagine this was like a slab or a raft, and I'm just splicing everything in the same place. Now, if I take this section, I'm looking here at this section. I'm cutting and looking. Think about this. Now, how much percent of the bars are spliced? Now, in this case, I have 100% spliced. You got the idea? Now, how would I not get 100%? Can I get less than 100%? Yes, of course. If I get, for example, so that means to me, this case is a Class B. So it is the poor class or the regular class, where you just splice everything at the same section, which makes it a weak section. It makes this section a weak section because you are just splicing all the bars together. Now, a smarter engineer, but it costs money and effort, would not splice everything together, especially more critical. So I would, for example, do this, and then come here and do this. So what's happening here is I'm staggering my splice. So at any section, of the splice, I have some of my bars being spliced, like this, and other bars not being spliced, like this one and this one. So in this case, if I just look at these 4 bars, I have exactly 50% being spliced, right? At this section, I have 50% being spliced. You got the idea? So this is how I would have a good splice. So this here, I'll call it Class A. Sorry. Class A. Now what's a Class A? It is of having a percent of my splice being 50% or less. That's a Class A. If it goes to 100%, that's a Class B. Now another part that also dictates whether it's Class A or B is AS provided divided by AS required. If it is more than 2 or less than 2. Okay? So now at any section of the splice, I need to know how much demand do I have? What's MU? Right? We can put it this way. I have MU compared to versus phi MN. Now, if I'm getting my splice at the maximum moment, that's a really, really poor location for splicing, right? Because if you splice at the maximum moment, this is the place where you really use all your AS required, right? So this ratio will be about 1. So you're always a Class B, right? But if you get away from the maximum moment, for example, if I'm drawing this, and here's my moment, it goes up here, goes down, goes up, right? Now, within this area, this is where the 0 moment comes, I can freely do my splice because I know that the moment almost dies. So if the moment almost dies, I will always be closer and closer to my provided steel being more than double or near the double of the required steel. And then in this case, my splice could also be a Class A splice. Now the same information but in a different table, that's in chapter 10. It tells you if the tensile strength of the bar, stress in the bar, is less than 50% F yield and less than 50% of the bars are spliced at the same section, that's a Class A, which means you're applying some staggering, right? Otherwise, it's Class B, and if it's more than 50% F yield, then in all cases it becomes Class B. This is how you define the difference between a Class A and a Class B. As a detailer, how you put your reinforcement and location of your splices, this is where you can specify it being Class A or Class B. Lab splices of, this is 2011, of deformed bars in tension shall be Class B. They shall be Class B. So the first option for me is a Class B, except if these 2 conditions are satisfied. What are those 2 conditions? The area of the reinforcement is at least twice that is required by analysis over the entire length of the splice, okay? Or 1/2 or less of the total reinforcement being spliced within the lab section. Right? Remember, if you splice everything at the same section, you're definitely Class B. If you start staggering, you're Class A, and then you start looking at the stresses, and that dictates whether you're Class A or not. What's the beautiful thing about Class A is your LST will be equal to, for Class A, just LD. This is Class A. Now, if you ended up being Class B, then what happens? Then your LST equals 1.3 LD. Again, you always also compare to 300. You always compare to 300 millimeters. Okay? So make sure that you remember these 2 differences between them. If the bars of different size are lab spliced in tension, LST shall be the greater of LD of the bar, of the larger bar, and LST of the smaller bar. What does that mean? It means if I'm doing this, if I have a bigger bar, I'm going to exaggerate in the view now. I have a bigger bar coming from this side and a smaller bar coming from this side. Does that happen? Of course. Now I'm splicing, for example, phi 16 with a phi 13. What is the development length here, or the splice length here, going to be? What is this going to be based off? LST. Now this provision tells you that if you're splicing two different bar sizes, your splice length is the bigger of LD for this guy and LST for this guy. So you take the bigger of LD for the phi 16 and LST for the phi 13. This is what you apply for the splice, because you have two different bars, right? Two different bars, that means dB is different from one bar to another. Now for an exterior column, what is an exterior column? This is the end of your frame. So your beam stops here. It cannot continue afterward. This does not exist. So your bar must be bent. Or if your column is wide enough, then you can just get it straight with an LD. In this case, your development length becomes an LDH. That's a hook development length. And it starts from the face of the column. So starting from the face of the column, you calculate LDH. This is for the negative moment or the top reinforcement of the beam. Now for the interior column, which your beam is considered continuous, it continues to another beam here. In this case, your LD starts from the face of the column, but you have the chance to make it straight. And in this case, it becomes what? It becomes a tension splice. Why is it tension? Because this is top reinforcement for a negative moment, so it is subjected to tension, and that's LD in tension. Where do I stop that reinforcement in the middle of the beam? They said find where your point of inflection is. What's the point of inflection? The point of inflection is where your moment dies and goes down to zero. So it goes like this, right? This here is your point of inflection, where your moment flips from negative to positive moment. Okay, depending on how you draw it. Some schools draw it the other way around like this, and that's fine as well. This is the point of inflection. So once your point of inflection is known, which is this point, then that distance becomes d 12 dB or ln over 16, whichever is greater, for at least 1/3 of your area steel. So at least 1/3 of your steel must continue to this point. Again, imagine that I have, for example, 6 bars in the top steel. Here's my top steel. I have 6 bars. 1/3 of the 6 bars is how many bars? 2 of them. At least 2 of these bars, so could be 3, could be 4, could be all 6, must continue to this point. Where is this point? You find your point of inflection. You go beyond the point of inflection for a D, that's the depth of the beam, 12 dB, so that's the diameter of this bar times 12, or ln divided by 16. Ln is the clear distance of the beam, divided by 16. So the biggest of those guys, you have to continue your bar. In other words, if I get back here and I say, do I really need to put the top reinforcement like this, all of it? The answer is no. Only 1/3 of it needs to go beyond this by that distance, d 12 dB or ln divided by 16. And that is here. Now over here it will be AS. Over here, at least AS divided by 3. I'm sorry, AS divided by 3. Okay? So make sure that you understand this. You don't have to get all your steel passing beyond the point of inflection. You can only have 1/3 of it passing beyond the point of inflection. Now, how do I stop my reinforcement?
Now you're saying that 1/3 continues. How about the other 2/3? Now the next slide explains this. How do you continue your bars depending on the magnitude? This is what is in this slide. For what we call the curtailment of reinforcement, which means I'm stopping some of the bars and continuing others. And the reason for that is because I don't need them anymore. The capacity could drop because my demand drops. Imagine that I have high demand on one side here. You can imagine this is the top reinforcement, so this is a negative moment. That one here is the positive moment. If I have here two parts of the bars, so imagine that I have here, as I said in the example, I have 3 bars that will continue and 2 bars that will stop. If those are bar B, now bar B shall stop after your point of inflection, which is the point of 0 moment. So this here is 0 moment, by a distance equals d 12 dB or ln/16, as we said in the previous slide. Now that bar B capacity starts at where it is not needed anymore. So I don't need all 5 bars. All 5 bars used to resist that big moment. Now only 3 bars will resist that small moment. Now from that location where I don't need all 5 bars, I only need 3 bars, my bar B should extend for more than LD. And in this case, I compare those 3 numbers to that number, and whichever is bigger will dictate where the end of my bar B will be. Now, where does bar A stop? Bar A stops at the bigger of LD from the face of the support. That's where we need all 5 bars. Or D or 12 dB from where I only needed the 3 bars, where those 2 bars are not needed anymore. So this is where the top reinforcement curtailment goes. Now, if you tell me that I'm not going to stop anything, I'll just continue all 5 bars, then what really dictates would be this criteria, that you pass the point of inflection. In case you're just stopping all the bars together, then the point of inflection is going to be your reference, because you don't have LDs from demand capacity comparisons. Let's get to the bottom reinforcement. For the bottom reinforcement, at least 1/3 of AS, at least 1/3 of your area steel shall continue all the way to the support. In this case, when it comes to the support with a negative moment, it becomes under compression, and in this case, this distance becomes LD compression. So you have to pass the support face by compression length of development. Now, how about the amount of steel that I'm stopping here? Imagine that I have some, for example, 2 bars down here that continues all the way to the end. That's bigger than half, and 2 bars will stop. Where do I stop those 2 bars? Is at the biggest of the 2 distances, LD from the maximum moment, or D or 12 dB from, what is this point? It's the point where your moment strength of the bars A continue. What are the bars A? These are the bars that will continue all the way to the end of your span. So because now I need the strength of bar A, for example, I dropped from 400 kilonewton meter to 200 kilonewton meter. Where I don't need the 2 bars anymore, I have to extend them by a D or 12 dB, whichever is bigger. Now, with examples on this, you would understand more on how we stop reinforcement and how we detail it. But generally speaking, where you don't need the bar anymore, you have to extend it at least a D or 12 dB. Because you have to ensure that even after I don't need them anymore, they are still there for some distance. So this is basically how the detailing based on ACI is required for curtailing the steel.